Sometimes the universe announces itself not with light, but with a small mismatch. Galaxies rotate like vast islands of stars. Near the center, gravity is strong. Farther out, where the stars are more spread out, astronomers expected the outer regions to move more slowly. But many galaxies did not behave that way. Their outer stars and gas were moving as if much more mass was present than telescopes could see. Something invisible seemed to be adding gravity. That missing ingredient is what we call dark matter. The name can sound mysterious, but the basic idea is simple. Dark matter is not dark because it is made of ordinary material hidden in shadows. It is called dark because it does not appear to give off, absorb, or reflect light in the usual way. We infer it from its pull. The evidence does not come from one galaxy alone. Astronomers see similar gravitational fingerprints in galaxy clusters, in the bending of distant starlight, and in the large-scale structure of the universe. Together, these clues suggest that ordinary atoms are only a small fraction of the matter shaping cosmic architecture. What is known is powerful. There is more gravity in the universe than visible matter can explain. What remains uncertain is the deeper identity of dark matter itself. It could be a kind of particle we have not detected directly, or the answer may point to something more surprising in physics. That uncertainty is not a weakness. It is why the discovery matters. Dark matter reminds us that astronomy is not only about beautiful objects glowing in space. Sometimes the most important thing in the cosmos is recognized by what it quietly controls. The memorable takeaway is this: galaxies may shine because of stars, but they seem to be held together by something we still cannot see. And that leads to another kind of invisible messenger crossing the universe. A particle can cross a wall of lead, a planet, and even your body while leaving almost no trace. These particles are called neutrinos. They are sometimes described as ghost particles, not because they are supernatural, but because they barely interact with ordinary matter. Trillions pass through us every second, mostly from the sun, and we do not feel a thing. For astronomers, that strange property is a gift. Light is the main tool of astronomy, but light can be blocked, scattered, or changed on its journey. Neutrinos can escape from places where light struggles to get out the hearts of exploding stars, the regions around feeding black holes, and some of the most energetic environments in the cosmos. The challenge is catching them. Because neutrinos almost never interact, detectors must be enormous and patient. Observatories such as IceCube use clear Antarctic ice as part of the detector. Scientists watch for rare flashes produced when a neutrino finally hits a particle in or near the instrument. Most of the time, nothing happens. Then once in a while, a tiny signal appears. What is known is that neutrinos come from the sun from cosmic ray interactions in Earth's atmosphere and from a famous nearby supernova observed in 1987. Scientists have also detected high-energy neutrinos from beyond our galaxy, opening a new way to study the universe. What is still uncertain is exactly which cosmic engines produce many of the highest energy neutrinos. Some may be linked to active galaxies with supermassive black holes, but the full picture is still being built. This is why neutrino astronomy feels so powerful. It does not replace telescopes. It adds a new sense. The takeaway is simple. The universe is not only sending us light, it is sending particles that can cross almost anything, carrying messages from places we cannot directly see. And there is another messenger that is not a particle at all. Space can ripple, and in 2015, humanity detected those ripples directly. For the first time, they are called gravitational waves. Imagine space-time as the stage on which everything happens. Planets orbit, light travels, galaxies drift. When extremely massive objects accelerate, especially black holes or neutron stars spiraling together, they can send tiny waves through that stage. By the time those waves reach Earth, they are unbelievably faint. They do not shake buildings. They do not make sound in the air. They stretch and squeeze space itself by an amount far smaller than an atom across instruments several kilometers long. That is why the discovery was so extraordinary. Observatories such as LIGO use laser light traveling down long tunnels to watch for a nearly impossible change in distance. When two black holes merge far away, the signal arrives as a brief pattern, a rising sweep, then silence. Scientists compare that pattern with predictions from Einstein's general relativity. What is known is that gravitational waves are real, and they have now been detected from multiple compact object mergers. They have revealed black holes in pairs, neutron stars colliding, and events that cannot be studied fully with light alone. What remains uncertain is the full population behind these signals. How do all these black hole pairs form? How often do neutron stars collide across cosmic history? Are there kinds of gravitational wave sources we have not yet recognized? The power of this field is that it gives astronomy a new sense of motion. Traditional telescopes collect light. Neutrino detectors catch rare particles. Gravitational wave observatories listen to the changing shape of space-time. The next step is not one single answer. It is a wider network, more sensitive instruments, and a growing library of cosmic collisions. Each detection helps scientists map the invisible lives of massive objects. The takeaway is this: the universe is not silent. Some of its deepest events travel to us as ripples in space itself. And together, these hidden clues are turning astronomy into something bigger than seeing.